Question 5 is a shortest route question, Dijkstra's algorithm. You read through it, it talks about a fare coming to town and sets up rides in 2 large fields, the fields here being depicted by these squares. 10 rides in total, 5 there, another 5 there. The weights are the time in minutes it takes to walk between each of the rides, and there's a footbridge from D to F, which is the only way of joining the fields, of getting between the 2 fields. Use Dijkstra's algorithm to find the minimum time to walk from A to each of the other rides. So we're going to have to carry on with Dijkstra's starting at A until there's a permanent label on every vertex. You need to be really careful with this. From looking at the way that the Dijkstra's question, this question was marked last year, you couldn't really afford to make any mistakes without losing a lot of these marks, if not all of them. So make sure you are very precise about how you label it. So we start off with a 0 at the start vertex and we box it. We now put temporary values everywhere we can get to directly, so the 3 vertices we can get to directly from A, 5 at D, and 8 at C, and 4 at B. We now look for the shortest or the smallest value, shortest route from A, and that's the 4 at B. We know it can't be beaten because the only alternatives are to go through other vertices, and we don't have negatives in these style of problems when we use Dijkstra's. So we box the 4 at B, that's now permanent. We now need to look at where we can go from B. Well, clearly A is already permanently labelled, so we don't investigate that. 4 plus 2 to C is better than 8, so we cross out the 8 and replace with 6, but make sure you cross it in a way it's still visible. And you can also go from B to E, which is 4 plus 8, 12. That's all we can do from B, so now we look round the whole graph again for the smallest, and it's the 5 at D. We now investigate where we can go from D. Well, again, not to there. We could go to C, but 5 plus 4 is 9, so that's no better than 6, so we ignore that. 5 plus 2 gives us 7 to F. 5 plus 6 gives us 11 at E, which is an improvement on 12, so we put the 11 there. We now again look for the smallest, and it's the 6 at C. So really careful as you go. The only place we can get to from C that isn't already permanently labelled is to E. 6 plus 3 is 9. So again, a further improvement at E, better than 11, so we do that. That's all we can do. So again, we now look around the whole graph for the smallest working value, and it's the 7 at F. We now investigate where we can go from F. Well, 7 plus 5, 12 to I. 7 plus 3, 10 at H. 7 plus 7, 14 at G. That's all we can do. So again, we look round the whole graph for the smallest, we pick out the 9. We've now completed the first field. Nowhere we can go from E that isn't already permanently labelled, so once again we go to looking for the smallest temporary value, and it's the 10 at H. Where can we go? Can't go there, permanently labelled. 10 plus 4, 14. It's no improvement on 12. 10 plus 5, 15. 10 plus 3, 13 is an improvement, so we do that. That's all we could do, so we now again look for the shortest, and we box the 12 at I. 12 plus 3, 15, so that's no improvement, so we don't bother with that. Nothing else we can label, so the 13 now gets labelled. 13 plus 3 is 16, no improvement, so finally we box the 15. We've now boxed, permanently labelled every vertex, so we've finished. So the first part of the question, find out the minimum time to walk from A to each of the other rides. So we've done all that. Write down the route corresponding to the minimum time to walk from A to G. That's 13. To find the route, we backtrack. We subtract the permanent labels to see if they come to the same as the weight on the edge. 13 minus 7 is 6, so clearly that isn't part of the route. 13 minus 10 is 3. So we could go to H. We'll investigate other possibilities just in case there's a second route, but clearly that doesn't work. So we're now at H. 10, that's not going to work. 10 minus 7 is 3, so that takes us to F. Remembering we're working backwards here. Clearly we have to go F to D, so that's 2 there. And then D to A, 5 minus 0 is 5. And there you have your route and the value. And again, don't forget the units of measurement, it's in minutes. For part B, it says the following year the fare returns. But this time they add a second footbridge between E and G. So a footbridge here. This reduces the time taken to get from A to G, but the time taken from A to J is not reduced. So if we call E to G X, find two inequalities and hence state the value of X. Well, for the first criteria, it reduces the time taken from A to G. Well, here, to get to G here, previously was this way and had a value of 13. It takes us 9, shortest route to E, so that means that it must be, if it's less, it means it must be X. In order for this to be better, must be less than 4. A to J is not reduced. Well, A to J here, where you can see here that J is 15, so that would mean that this would need to be shorter than these two ways of 15. So it has to be, it could be equal to, so it could be equal to 3, which would make this 12 and that then 15, but it has to be at least 3, so greater than or equal to 3. So that implies, well, it's greater than or equal to 3 but less than 4, that X must equal 3. And again, remember it's minutes. And that's it. So 8 marks. Quite often get things a little bit like that coming up in these exams. But my main bit of advice on this, having seen how this was marked last year, is be really, really careful with your labelling. I'd seen a couple of examples of students' works where they'd made very little mistakes and they'd still been penalised really, really badly. In fact, in both instances got no marks. A couple of little mistakes and that was enough to lose them all the marks. So be really, really careful that you're labelling it properly and carefully. It needs to look exactly like this with the right numbers crossed out and boxed.